Subhadra madam, are you there? Subhadra ma'am?
Yes, ma'am.
Subha ma'am, the speaker wants the link once again. You please mail him. Mail the
Okay.
Zoom link to his mail ID.
Okay, ma'am.
Good afternoon, ma'am.
Good afternoon, all of you. Kindly mute your microphones. மைனாவதி உங்க மைக் ஆஃப் பண்ணிக்கோங்க. பிரியா மேம், மைனாவதியோட மைக் ஆஃப் பண்ணி விடுங்க. Subha ma'am, check it once again. Try to mail once more, Subha madam.
Okay, ma'am.
Good afternoon, sir. Welcome to this conference, sir. Host, please unmute speaker's mic.
Now, madam? Now is it okay?
Yes, sir. Yes, sir. Your audio is clear, sir. Yes. Good afternoon, sir. Welcome to our national conference.
Okay, thank you, madam. Then,
Sudarshana, madam.
Don't wait until the conditions are perfect to begin. Beginning makes the condition perfect. Welcome back to the session 2 of the National Conference on Advanced Functional Materials and Engineering. Small cheer and great welcome makes the manifest. May I now request Dr. T. Vasudevan, Associate Professor, Department of Physics, to lift the camera and introduce the speaker of the session.
afternoon to one and all present here. A warm welcome to you all. It's my immense pleasure to introduce our chief guest of this session, Dr. T. Demappa, Professor, Department of Postgraduate Studies and Research in Polymer Science, University of Mysore. Sir M. Visvesvaraya Postgraduate Center, Industrial Area, Tribunakere, Mandya. He has completed his UG degree in the year of 1987 and PG degree in the year of 1990 at University of Mysore. He has also completed his PhD degree at the same university in the year of 1998. Title of his thesis was Oxidation of Substrates with N-metallo N-aryl halo sulfonamide, a kinetic study. He has done various researches in the field of chemical kinetics, redox polymerization, synthesis and characterization, polymer blends, polymer composites, synthesis of copolymers, polymer grafting, hydrogels for biomedical applications, drug delivery, synthesis of edible polymer films for food packaging applications, synthesis and characterization of polymer flocculating clarification agents in sugarcane juice clarification, electrical, thermal, mechanical, and optical properties of polymer composites and polymer nanocomposite films, microstructural and radiation effect on polymer blends and composites. From 1993 to 1995, he was worked as an UPGR Junior Research Fellow under the guidance of Professor S. Ananda in the Department of Chemistry, Manasa Gangotri, University of Mysore. From 1995 to 1997, he was worked as a Senior Research Fellow in the Department of Chemistry, Manasa Gangotri, Mysore. He has gained a lot of experience by working as a lecturer in various institutions between the year 1997 to 2003. Then he has been promoted as a professor, Department of Polymer Science in the year 2014. He has completed 3 refresher course and 1 orientation program in the year 2002-2009. So far, he had published 68 research publications and presented 126 papers in various international conferences. He has successfully guided and produced 4 PhD scholars, 3 MPhil scholars, and 1 postdoctoral degree. Currently, 2 PhD scholars are working under his guidance. He had received Rashtriya Shiksha Ratna Award from Council for Economic Growth and Research at New Delhi in the year 2007. He had also honored with Dr. Abdul Kalam Lifetime Achievement National Award for the remarkable achievements in the field of teaching, research and publications. In the year of 2010, he was sanctioned a sum of rupees 1 lakh for his completion of a minor research project entitled Miscibility Studies of Water-Soluble Polymer Blends using Density, Refractive Index, Ultrasonic Velocity, and Viscosity method by UGC, New Delhi. His professional affiliations are life member of an Indian Council of Chemists and life member of Mysore University Teachers Association, Mysore University Postgraduate Teachers Association, and member of board of BOS in Polymer Science 2009, University of Mysore, and member of BOE in Polymer Science, University of Mysore 2007. He has been a adjudicate for 13 PhD theses and 3 MTech dissertations. He has delivered 13 invited talks and 4 special lectures in various educational institutions. He has guided more than 147 MSc students for their dissertation works. He has visited several countries like Seoul, Shanghai, Singapore, Malaysia, and South Korea. Such an eminent person is with us. Please make use of this session. Thank you.
Thank you, ma'am. Thank you for the brief introduction. I feel overwhelmed to invite our speaker for the session 2, Dr. T. Vemappa, Professor, Department of Postgraduate Studies and Research in Polymer Science, University of Mysore, Sir M. Vishweshwaraya, Postgraduate Center, Manya, to take over the session. Sir, session is over to you, sir.
Aruljori madam, kindly unmute the speaker's mic.
Okay. Now it's okay, madam?
Yes, sir.
Okay.
Now it is okay.
Okay, thank you very much, Professor T. Vasuki, madam, for nice introduction. First of all, I would like to thank the Bharatiya University, Tamil Nadu, organizing this wonderful webinar. I would like to thank Dr. D. Maithili, Principal, P.K.R. Arts College for Women, uh, and I would like to thank also Dr. V. Radhika, the convener and the head of the Department of Physics, Bharatiya University, Tamil Nadu. Thank you, madam. Thank you. And also, I would like thank to Professor Jagata Lakshmanan, Chief Executive Officer. And also, I would thank all the delegates and participants and students of this webinar. And finally, thank you one and all. Thank you. Just okay, is it okay, madam, or it want to
It's okay.
slideshow?
It's okay,
Or?
sir. It is clear, sir. It is visible.
Okay, okay, thank you. Okay. Shall I continue?
Yes, sir. Yes.
It is
Yes,
audible
sir.
and
Please.
visible. Okay, madam, thank you. Okay, my topic is advanced functional materials. I told you know it's a very suitable and wonderful topic nowadays. Just what is the definition and just introduction to some areas of advanced functional material. It take more than 1 hour just by mention the areas of advanced functional material. So I'm drop here itself. I'm not going to even have to mention the areas. If you interest, if time permits, I would like to say for inspire the students for young research buds, at least some areas of new areas if time permits. Just I starts my topic. Okay, this is advanced functional material. Uh, okay, this topic includes structural, thermal, mechanical, electrical, and optoelectrical properties of polymer composites and polymer composite films. Okay, I am take two of my research work, two component of my research work. One is polymer composite and polymer composite films. Okay, polymer composite, it's it is nothing but what is called the two component system. The one is the major component, that is the matrix, and another one is the reinforcing material. That is the definition of polymer composite. More than that also possible. Minimum is two components. More than, depending upon the processability, customer specification, tailor-made properties, tailor-made applications, we go for what is called additives, plasticizer, colorants, okay, like that. I here use two components I already told you. Polymer composite, it includes in this study the fiber reinforced plastic I have taken. The fibers here are the HDPE, high density polyethylene we use as a fiber, that is reinforcing material. Whereas here the matrix is epoxy. Okay, I used one more reinforcing material, that is hybrid. More than that, I will call it as a hybrid reinforcing material, hybrid composites. I used clay as a reinforcing material. It is a particulate in nature. Its range is 0.1 to 0.7 PHR, that is parts per 100 resin. More than that, it is possible because it cannot be processed. 0.1 to 0.7 is the maximum. More than that, it cannot mix, it agglomerates. That's why I fixed for the restricted to 0.7 PHR only. By mixing this, we fabricate a composite material that is in the form of a laminate. Because we use the clay, it is in the laminate form, laminate structure that is layer by layer material. That's how we call it as a laminate composite. We fabricate laminates and they were tested for so many properties, say structural, thermal, mechanical. Okay, and important one is fire resistant or fire retardant properties are the important characteristics of this material, our research material. Okay, that it comes to what is called polymer composite. I mean, do not confuse polymer composite and polymer composite films. Usually, polymer composite, I will give you the best example for students. The best example is RCC, reinforced cement concrete. Okay, where cement has the what is called matrix, major component, and iron rod or iron bars are the reinforcing material, and gravels is another reinforcing material. So composite is a bulk material. It requires more product to process or to made end product. Okay, like that, the final product or customer specification. The samples required a bulk, a more compound voluminous product is required. Whereas come to the polymer composite films, the composite films are made by a polymer dissolved in a suitable solvent, and reinforcing material will also common solvent. Then you have to evaporate. Then you will get a solid film that is called the composite film, polymer composite film, a thin film, minimum zero point 0.5 millimeter thickness. So for this preparation or this for characterization, a meager sample is enough, not bulk material. That is the difference between polymer composite and polymer composite films in my study. Okay, polymer composite, we studied mechanical properties and the thermal properties, and this is and also the flame retardant properties. Whereas polymer composite films, that is a polyelectrolyte, that it conducts electricity also in the what is called liquid form and solid form both. I will take hydroxypropyl methyl cellulose as a matrix. So HPMC, hydroxypropyl methyl cellulose, it is a totally biodegradable and water soluble, and also what is called non-ionic polymer, and it is edible polymer also. Edible polymer means we can eat the polymer along with the food packaging material. I published the paper on hydroxypropyl methyl cellulose in food processing and preservative, the Journal of Food Processing and Preservative. That means we can eat that HPMC polymer food packaging material along with That means it is non-toxic. Okay, this film were also used to characterize the structural properties, electrical properties, and optoelectrical properties, and thermal properties, and some radiation properties also studied. Okay, XRD results reveal that the amorphous domain of HPMC polymer matrix were increased with increase of sodium iodide inorganic salt concentration. Usually all polymers are semi-crystalline in nature. So this is crystalline nature, HPMC. So entropy is very less rigid. Then we add a plasticizer or a reinforcing material. Then the crystallinity will disturb. It shifts crystalline to amorphous or glassy state. That means entropy increases. So the flexibility increases, elasticity increases. The movement of ions, atoms, or molecules are easily moving. Then electrical property, magnetic property, and so many other properties will enhance. Here, the degree of crystallinity was studied, okay, and the thermal stability, thermal resistance, and other properties were studied by DSC, differential scanning calorimetry, and thermal gravimetric analysis. I will explain in detail in the next slides. Okay, from the film, composite film, direct current and that is AC current and DC current. We use LCR bridge of DC current and AC current. LCR bridge. We measured electrical conductivity varying with the temperature and optoelectrical properties by UV spectroscopy were studied. Okay, that is optical electrical properties. That is direct band gap and indirect band gap were calculated using what is called UV spectroscopy. A simple UV spectroscopy. You can study or do research on this very simple and typical research. So, if the any metal ions, inorganic salts, or nanoparticles we incorporate, then the energy band gap, optical energy band gap decreases, hence the electrical property increases. That can explain in the next slide. Research method or experimental method. What are the materials we are used for? Especially first one, that is a polymer composite we are talking. Okay, for polymer composite, FRP composite, fiber reinforced plastic, the first FRP was used by Dr. APJ Abdul Kalam for aeronautic applications. Here, the matrix, that is epoxy resin of grade MY740, and the accelerator, that is curing material, that is K112, and order were also used, that is another HY918. These, depending upon the what is called epoxy grade, a suitable order is also very important for the selection of this combination is very important. These materials are procured from Huntsman Advanced Materials Private, Private Limited India. And come to the fiber reinforced material. Fibers, the fibers are the polypropylene and HDPE. Okay, both the fibers are used. These are obtained from Reliance Industry Limited India. The average fiber length was 3 millimeter and average diameter was 40 micrometer. Okay, that is the fiber. And another reinforcing material, that is clay, organic organo-modified clay. It is also called as chloricide 30B. It was procured from Southern Clay Products USA as a gift sample. The average particle size as given by the supplier was 10 micrometer. and its density was 1.98 gram per centimeter. All the chemicals used were as such without modification or without purification. We use all these chemicals as such. Then preparation of composite laminates. Okay. First polymer composites. That is, initially clay and polypropylene short fibers were mixed with 100 pH epoxy and stirred for 30 minutes at 1350 rotations per minute. That is the speed using a conventional variable speed tanko stirrer of Japan model. And then one P.K.R accelerator, that is K112, and 85 P.K.R of hardener were mixed with epoxy polypropylene clay, that is ternary mixture, for another 5 minutes at the same speed. Then the contents were transferred to a Teflon mold of the size 200 millimeter, 100 millimeter, and 3 millimeter. The samples were cured at 100 degrees centigrade for 2 hours and post cured at 120 degrees centigrade for 4 hours. Then characterization. These samples of 100 millimeter into 200 millimeter into 300 millimeter, they sheet like a product after detecting from mold, Teflon mold. Then we cut the specimens according to ASTM standards for tensile strength, impact strength, and tensile modulus, flexural test, like that. You see, these are the ASTM standard for impact test, ASTM D256. Okay. Similarly, tensile test ASTM D638. Flexural test like this. And tensile test was done with a stress range of 3000 megapascal. On the strain range, we are around 300%. On the speed of about 5 millimeter per minute. Okay, whereas flexural testings were conducted at least minimum 3 points and take average. But here we mentioned 3, but we will try 5 different positions and take an average. Then the thermal properties, thermogravimetric analysis, TDA, was carried out using this instrument. The heating rate, that is the range of temperature, was fixed from 30 degrees centigrade to 650 degrees centigrade. By this range, our polymer composite will change at various stages. The heating rate was fixed for 10 degrees centigrade per minute under the nitrogen atmosphere with a flow rate 60 ml per minute. Otherwise, without inert atmosphere, that is nitrogen atmosphere, our compound will completely burn, left behind a white ash. So that's why it is heated in presence of inert atmosphere only. Okay, to check the flame retardant property, this is very, very important property. This material is a fire retardant or fire resistant material. These properties were checked by underwriter laboratories 94 tests. It was conducted by underwriter laboratory University of Protocol. Okay, and thus explanation was given in next slide. Morphological studies of broken after mechanical properties. Why after broken, that means maximum energy stress load we are applying where it is broken, then that mechanical properties were recorded. How the materials, that is components, are distributed, greenhouse are what is called distributed, that can be seen by environmental scanning electron microscopy of Netherlands. Okay, thermal properties, that is order stability, thermal stability, thermal resistance. And another one is degradation kinetics was also studied here. Okay. Okay, this is a table of thermal properties of epoxy HDPE clay, that is ternary composite, three component system. The composite material in the form of a laminate, because we are used clay as a laminate structure, that is layer by layer structures. Okay, come to this, this is sample. Without adding clay, only 5% of epoxy and 5% of HDPE, that is fabricate and that material. When subjected to heat from 30 degrees centigrade to 650 degrees centigrade, within this range, the our material changes, so many changes in various stages. Okay, then at 5% of weight loss is found to be 218 degrees centigrade. It is called the initial degradation temperature, or it is also referred as the thermal resistance or thermal stability of that compound. Okay, that is when it reaches 218 degrees centigrade, then it loss or loses 5% of its original weight loss. Okay, the same compound, it loses 10% weight loss. The temperature is required 309 degrees centigrade. Okay, that is, this is the temperature at maximum rate of degradation in degree of what is called Celsius. This is 388 degree requires. Then this is what is called total degradation. Percentage of weight loss is found to be 47.1 per minute. Okay, this is weight loss per minute. This is this. Then energy of activation also calculated. That is, there are two methods. One is Horowitz method. The energy of activation is 30.765 kilojoules per mole. That means the energy required for, that is, one molecule of the compound decomposes, the energy required for 30.765 kilojoules per mole. Whereas Freeman and Caron has 29.230. Whereas order of the reaction is found to be 0.631. Okay. Then we add 0.1 P.K.R of clay, zero point 0.1 parts per 100 resin. You see the thermal stability of the compound with withstand temperature tremendously increases. It is noticed that tremendously increases. 218 here 289, that is 71 degrees centigrade is rise increases. That means it reaches, thermal stability increases 71 degrees. Same at 10% weight loss is required for 325 degrees centigrade. Okay, like this. You see that is a total maximum degradation in weight percentage is 112. You see that is 47.1, here 111.2, 111.2. That means that temperature stability, thermal stability increases. So you have to, same energy of activation is little bit, very negligible amount of the energy of activation is less than neat compound samples here also. Okay, whereas come to the 0.2 P.H.R, that is 276 degrees centigrade, little bit decreases. Okay, then the 323, that is 379. You see, it still further increases. That is rate of degradation. That the temperature required increases. Here the energy of activation little bit increases. Here also increases. Order of the reaction is 0.765. If the 0.3 P.H.R decreases. After 0.2 to 0.3 onwards, it is decreases. Here also after 0.3% of P.H.R decreases. Here also decreases. Energy of activation. These are all the some inconsistencies there. This is because of what is called, when temperature increases, the oxides of clay, modified clay oxides will form, that it will enhance the degradation. Degradation increases. That's why this is what is called anomaly or inconsistency. Okay, that is. Whereas the acceptance of this model, two models were completely accepted because the regressional analysis 0.996 in Arrowitz-Metzger equation and the Freeman-Carroll equation 0.987, 985. So both are acceptable. That means it indicates that if the clay increases, the thermal stability increases up to 0.2 because of its the what is called the interfacial adhesion or interfacial interaction between the clay and the epoxy increases. Afterwards, it is decreases. That's why the thermal stability increases if you are adding clay. You see, without this one, the thermal stability increases. This is thermal gravimetric analysis. I told you know the heat subjected to 30 degrees centigrade to here see 650 degrees centigrade, 650 degrees centigrade. Okay, the heating rate was 10 degrees centigrade per minute. But these curves are fused together. It cannot be isolated. So the table itself gives the more information. Then for kinetic study, thermogravimetric analysis in the previous previous what's called figure or graph, the heating rate was 10 degrees centigrade per minute. We calculate the degradation kinetics IDT for 5% weight loss and 10% weight loss. That was calculated energy of activation and order of the reaction by Horowitz-Metzger equation. This is the equation used for to calculate what is called the energy of activation and order of the reaction itself. You see, ln 1 over 1 minus alpha it is equal to energy of activation is the T square, where this is taken as y-axis, theta in x-axis. We plot a graph, we find a straight line. The slope gives you the energy of activation, okay, and the intercept that is gives the what is called order of the reaction. Alpha is the heating rate that is 10 degrees centigrade per minute. Whereas theta is equal to T minus T, where T is the temperature at the time T. Where T is the temperature at W by W naught means W is the weight at time T and W naught is the initial weight. Okay, this is another equation, Freeman and Carroll equation, I told you. That is the delta logarithm of dW by dt. That means if the or weight, degradation weight, loss of weight with respect to time. Okay, this is what is called weight loss at the completion of the reaction. Okay, we want that is energy of activation E, and this is the order of the reaction. We plot a graph of this one on y-axis and only this one on x-axis. We plot a graph, then we get a straight line. The slope it gives you the energy of activation, and intercept gives you the order of the reaction. You see, this is the ln 1 over 1 minus alpha. That is Horowitz-Metzger equation. Okay, theta on x-axis, straight line. If you take a slope y by x, it gives you what is called energy of activation EA, and intercept this gives you order of the reaction. See another Freeman and Carroll kinetics model or method. This is also logarithm of dW by dt into logarithm of WR divided by 1 over t into logarithm WR. We approximately we get a straight line. To take a slope, okay, even we don't get straight line, if it is not, we can take tangent to that, then we calculate the slope. Okay. Then slope gives you the energy of activation EA, and intercept is extrapolated to that, that is gives you order of the reaction. Then come to the structural studies. Thermal studies over, and this is the structural studies by XRD. You see uh, HPMC and sodium iodide inorganic material used in complex or doping. Okay. Then you see, I am interested in this one only. Okay. See, that is a melting temperature. Pure HPMC, that is 72.16 degree centigrade. If we add sodium iodide 1%, then there is a tremendous increase in stability, melting temperature 81.33 degrees. If you add 4%, then it still increases. This is the maximum. Afterwards, it is decreases. You see, if you add, metal ions, that is sodium iodide as a salt, inorganic salt, then what is called thermal stability increases, degradation, uh, initial degradation temperature. Okay, whereas the enthalpy of fusion decreases. This is for HPMC and the sodium iodide. I take one more inorganic salt of the same to the HPMC. You see cadmium chloride. You see pure HPMC 72.16 in the previous also, that is 72.16, because HPMC is a fixed for this peak temperature or melting temperature. If you add 1% of cadmium chloride, you see 83 degrees centigrade. If you add 4% of cadmium chloride, 1 or 2.5, the tremendous temperature stability increases. Okay, come to the mechanical properties. It is very important. Okay. So mechanical properties were first impact strength. Okay. The impact strength, this is a clay variation. You see, this is the percentage of clay variation 0.1 to 0.7. This is the maximum. I told you in the abstract, no. More than that, it is not possible to process. Okay. Then this is the impact strength in joules per meter. Without adding a clay, you see, this is the impact strength 45 plus or minus 1.22 joules per meter. This is the impact strength. If you add just 0.1 phr of clay, you see the tremendous increases of impact strength, that is mechanical strength, 55 plus or minus 1.47 joules per meter. 0.2, this is the maximum impact strength, is found to be 65.8 plus or minus 1.52 joules per meter. Okay. Then 0.3 decreases, 0.4 decreases, still 0.7 decreases. The maximum mechanical, that is impact strength, is found to be 0.2 phr because of its what is called improved interfacial bond strength. Okay, interfacial adhesion between a clay and the epoxy. Okay, this one. Afterwards, there is agglomeration. There is no what is called a proper wettability between clay and epoxy resin. So there is agglomeration takes place. Big zone is formed, and it is not sufficient wettable means there is not. It is an improper curing takes place. Hence, the mechanical property decreases. This is what is called improper curing, and also agglomerates are tactile formation, and it doesn't withstand say energy load or stress. That mechanical energy cannot be tolerated. Then it is what's called collapse. It's a, what's called crack formation. Micro cracks will develop. Further loading on the what is called clay, then micro cracks will develop for macro cracks and collapse. Then come to the tensile strength. Tensile strength also what is called the same behavior. Okay. Then Young's modulus also same behavior. The maximum mechanical property or the maximum strength is found to be 0.2 phr only. That is megapascal. 640 megapascal. You see, this is without adding clay, 450 megapascal. You see the tremendous change will take place. I think definitely clay will play a prominent role to enhance the mechanical properties, no doubt. And this is Young's modulus. And then flexural strength will also behave same behavior. Okay. Okay. This is because in the lower clay loading, we find the tensile strength, the flexural strength, and Young's modulus. Okay, the composites they were high in the lower clay loading. This is because of improved interfacial adhesion or interfacial bonding or interfacial strength. Okay, due to the clay and epoxy. Okay, and why this is a decreasing means after 0.3 P.H.R. because of it's the same agglomerates, tectoids, and what is called without standing of what is called mechanical stride. The defects formation takes place, or flaws formation takes place, or crack formation is the major region for this. Come to the elongation property. Okay, here the elongation property is not markedly increasing or decreasing. It almost constant, but here it is not significantly increases, but very marginally increasing at 0.2 pH. This is. Whereas come to polypropylene, you will notice a tremendous effect. This is for instead of HDPE. Are you able to see the cursor movement? This is polypropylene instead of HDPE. You see the tremendous changes will occur. Elasticity decreases. Okay, you see elasticity decreases. It may be due to the rigidity of the clay particles or clay structures. Okay, it might be have limited what is called it restricted, it decreases, it diminishes what is called the plastic deformation of the plastic. Okay, that is HDP. Plastic deformation decreases. That's why it is decreases. And also it pull out from the fiber. Okay, another reason is if you go on adding clay, then it is pull out from the fibers. This is what is called elongation property. Oh, then mechanical properties over. Then the very important aspect is flame retardant properties. Okay, see this is a flame retardant property. If you subjected to burn the samples, we do the two methods. One is horizontal burning and another one is vertical burning tests. Underwriter laboratories 94 tests of various protocol. Okay, all horizontal burning tests were satisfied, whereas all vertical burning tests were failure. That's why this material is used for construction application, agricultural applications, and decorative applications such as the laminates, and it is not useful for aeronautic applications, space applications. Okay. See that is a burning test without adding the clay. Okay, the burning of our sample is 16 millimeter per minute. You see, this is 16 millimeter per minute. We have to able to burn the samples about 16 millimeter per minute. Where we add just 0.1 P.H.R of clay, you see that we cannot, burn, this length of sample, not 16 millimeter. Only able to burn 7.5 millimeter per minute. We are 0.2 P.H.R 7, 6.5 for 0.3 P.H.R, up to 4. You can imagine that 16 to 4. Okay, that means this is very, very important parameter, fire retardant material, just by adding clay to Flame retardant materials, we are used so many materials for organic materials. Take an example, aromatic compounds, aromaticity of the compounds. It increases melting point, boiling point, and flame retardant properties. And halogen materials are also halogen family, that is chlorine, bromine, iodine, fluorine, like that. And some nitrogen, phosphorus, phosphazine, borax, but they are hazardous to health. Okay, especially organic compounds, very strict VOC, volatile organic compounds, we restrict, but that is what is called the clay. It is not toxic, it is very cheaper. Okay, that's why I chosen for this as a clay material. It is tremendously decreases the what's called fire resistant material. Okay. Burning property will tremendously decrease. Actually, literature, the limiting value of burning is 75 millimeter per minute. But you can see that our material only this much. You can see 75 millimeter and this. So this is very useful for what's called flame retardant material, environmental friendly and economically viable. Okay, why this is decreasing means our clay composite consists of both carbon dioxide and water. Clay. When you subject it to burn, it dissociates to water and carbon dioxide. Carbon dioxide is a self-fire extinguisher. So the fire cannot propagate, even it cannot catch the fire after burning. It reduces the burning. And also when subjected to heat or burning, it burns and left behind a char. The char will do not allow the combustible gases contact with our material. So there is no contact between the combustible gases, including oxygen, and contact with our composite material. So it retards the combustion. And another one is what is called, it acts as a laminates barrier properties, barrier to the propagation of fire. So these are the factors. It reduces the what is called burning test. Come to the what is called morphological studies. How the particles are distributed, hence increase the mechanical properties and thermal resistant and fire resistant material. Okay. This is what is called pure without adding clay. You see the particles are equally distributed, mass, temperature, and all. Then 0.1 pH of clay, you see there is also increases the what is called thermal resistant and mechanical properties some extent up to 0.2 pH. This is 0.2 pH, that's the mechanical property increases because the what is called the distribution is dispersion is a good dispersion is space and addition between what is called the epoxy and the clay. The interfacial addition or interfacial bond is very high in this region. After 0.3 pH, what is called there is a agglomeration takes place and the cracks will develop. Okay, you see this is the cracks, you see this is the cracks and agglomerates on them. That's why the mechanical property decreases and other properties also decrease. Then structure properties for what is called composite films. Crystallinity, the degree of crystallinity is equal to AC divided by AC plus AA into 100, where AC is the what is called the area of crystallinity and the AA is the area of amorphicity or glassy, glassy state. Okay, that is a degree of crystallinity. You see, we studied HPMC and sodium iodide. The percentage of crystallinity, I want this only. degree of crystallinity. You see, pure HPMC is 65.29, whereas if you add 1% of sodium iodide, see the crystallinity decreases, the amorphosity increases. The crystallinity decrease means the entropy increases. Okay. Then the mobility, flexibility, elasticity increases. Similarly, the same HPMC and cadmium chloride, we see the crystallinity decreases. This is pure HPMC, this will decreases. If you go on increasing the inorganic salt, the crystallinity, the structure will changes. If you disturb the crystalline structure, amorphosity increases. Then the conductivity, electrical conductivity, and the mobility of ions will increase. This is the XRD study of HPMC and cadmium chloride. This is the pure cadmium chloride where you see the crystalline structure, the perfect crystalline. This is the pure HPMC. This is the semi-crystalline. Okay. If you add 1% of what is called cadmium chloride, 2%, 3%, and 4%, you see it completely the crystallinity, destroyed. Glassy state amorphous will exist. Okay, this is the evidence for that. Then come to the electrical conductivity studies. Usually polymers are insulating both electrical and thermal. Thermally insulating and electrically insulating. But we converted into electrical electrically conductivity. With the temperature dependent DC conductivity, there are two methods. One is LCR bridge with the temperature dependent and independent temperature dependent. Temperature dependent means if you go on varying the temperature, then the conductance, it gives you conductance. From that we derived electrical conductivity. Okay, this is the model we use electrical conductivity. DC conductivity from the DC conductometer, DC conducting LCA or bridge, we can use this equation to calculate the conductivity, where 1 over R into T divided by A, where T is the thickness of the sample, that means a film, 0.5 mm thickness. Actually, this is a manual made, it is not uniform. If it is made from extrusion or single extrude molds and some equipment, approximately they are equal. But these are all man-made, the thickness is varying. If the thickness is varying, the conductivity is also varying. You people, physics, you know that. The conductivity is proportional to the thickness of the diameter of the conducting material, not to length. Similarly, the thickness increases, conductivity increases. Where E is the area of cross section, that is approximately 2 centimeter is enough for what is called to calculate the electrical conductivity from conductance, DC conductance. Okay, this is the 2 millimeter area. Okay, from AC conductivity bridge, this is the formula for calculate the conductivity. This is the conductance. G is the conductance. Okay, D is the thickness once again, and A is the same. Okay, 2 centimeters. Some instruments they are 7 millimeters, sorry, 7 centimeters also different. Okay, this is the formula to calculate the conductivity from conductance. Here the energy of activation from Arrhenius equation. You know that. Okay. Okay, come to the conductivity of the film HPMC sodium. In the previous, the same material, HPMC, it is a polymer insulating material, non-ionic also. We add some sodium iodide crystals or salts to conduct electricity, the solid polymer electrolyte. Then at the varying temperature, the conductivity also increases because of its mobility of the ions. If temperature increases, mobility of the ions increases and the conductivity enhances. This is the two regions of what is called energy of activation in electron volts. Okay. You take pure HPMC, the conductivity is 6.530 into 10 to the power of 9 Siemens per centimeter. Okay, at this temperature, 30 degrees, sorry, 25 degrees centigrade. For 30 degrees centigrade, the conductivity increases. Here also increases. Whereas this is the energy of activation of region 1, region 2. So this is the pure HPMC. If you add 1% of sodium iodide, then you see the electrical conductivity increases 10 to the power of minus 9, 10 to the power of minus 8. So temperature increases, still increases energy of activation. I'm not bothered. So 2% of NaI, so further increase. So increases up to 4%. You see, this is 10 to the power of minus 9, 10 to the power of minus 5. That means if the sodium iodide salt increases, the crystallinity shift towards amorphous, then conductivity enhances. This is how the sodium iodide crystal will increase the electrical conductivity. This is used for solid batteries, rechargeable batteries, flexible batteries, EMI shielding. Right. The same polymer with inorganic salt is different cadmium chloride. So this is the pure HPMC. The electrical conductivity is 6.530 Siemens per centimeter. Okay. If the temperature increases, you see increases. This is 1% increases. You see this is increases. You see 10 to the power of minus 9, 10 to the power of minus 6. Okay, that is electrical conductivity increases with doping, okay, or complexity. Here, this is the conductivity. See, cadmium chloride. This is the 4% of cadmium chloride. This is pure, what is called HPMC. These are the variations of cadmium chloride, 4 samples. This is also energy of activation in the 2 regions. I am not interested. Okay. When exposed to radiation, the same film when exposed to radiation, what is its electrical conductivity? What is the effect on electrical conductivity? Okay, here this is unirradiated. Okay, pure sample without irradiated. You see, this is in the previous case 6.5 to 10 to the right. That means if the sodium iodide increases, electrical conductivity increases 10 to the power of minus 2, 10 to the power of minus 5. Okay. Then we subjected to radiation, gamma radiation, 20 kilograms. You see, without gamma radiation, your electrical conductivity, including NAI, is this much, 6.739 into 10 to the power of minus 8 Siemens per centimeter. Okay, when exposed to gamma radiation of the intensity that is 20 kilogray, then the electrical conductivity increases. Sorry, this is increases. Okay, 10 to the power of minus 8. If the temperature increases, this is without radiation, with 20 kilogray radiation. You see that increases. This is without, you see this is increase. This is without, see increase. Okay, like that you see that after 20 kilogram, this much, you see this increase. Okay, like that. Whereas in 100 kilogram, that is the increase 10 to the power of minus 5. You can imagine that 10 to the power of minus 9 to 10 to the power of minus 9, 10,000 times increases. Okay, it enhances 10,000 times. Okay, approximately. That means if exposure to gamma radiation, still the what is called ionization increases, free radicals will liberated, some charged species and atomic and subatomic particles will generate, then it will enhance the electrical conductivity. Then come to the optical properties, optoelectronic properties, UV absorption spectroscopy. I take polyvinyl alcohol and sodium chloride composite film I am used here. Okay. See, this is the, I am not interested. This is the nanometer for this one, pi transition. Sodium chloride is increased. The intramolecular hydrogen bonding is formation. Okay. This is I want. You see, this is absorption and wavelength lambda. Okay. So 0.1% of NaCl, you see the absorption. 0.2, 0.3, 0.4, 0.5% of NaCl. If the one increasing sodium chloride content concentration that is in gram, then the absorption increases. Okay. Then we plot a graph of what is called absorption coefficient. Absorption coefficient alpha is equal to what is called absorption divided by thickness of the film. That is called the absorption coefficient. Okay. Then absorption coefficient is multiplied by one quanta h nu, where h is the constant and v depending upon the frequency, that is the reciprocal of the wavelength. Okay. So h nu alpha into h nu, that is h nu, that is c by lambda, where c is the velocity of light and divided by each wavelength. Then you will get alpha into h nu to the power of n, where n is equal to 2, the optical energy band gap, that is a direct optical energy band gap. If the n is equal to 1 by 2, the optical energy gap is indirect optical energy band gap. Okay, that we calculate from the UV spectroscopy. Okay, this is the alpha, that is what is called absorption coefficient divided by thickness. This is the thickness. This is also possible in some journals and some method, but you take directly absorption divided by thickness, that is absorption coefficient alpha. Anyway, okay, that is energy of activation. That is you take alpha into h nu to the power of n on y-axis and h into nu, that is an x-axis in electron volt. Okay, we plot a graph, then extrapolate to x-axis, then the energy, optical energy band gap in electron volt. Okay, this is the equation for what is called energy. H Okay, this is the optical band gap of energy. You see, 1% sodium chloride, then 3.84 electron volt. This is direct energy band gap. That is indirect energy band, optical energy band gap, 2.4 electron volt. If you go on adding the sodium chloride, the energy band gap, optical, I'm saying optical energy band gap decreases. That means if the optical energy band gap decreases, electrical conductivity increases. That means the more absorption of energy, light, UV light or any white light, it is sufficient to generate electricity. That is what's called optoelectronic properties of the polymeric material. They are used for what is called rechargeable batteries, flexible batteries, and alkali batteries, like that. Okay. You see how you see alpha into h nu whole square, that is a direct band gap versus h nu in electron volts. Okay, that is electron volts meters per square. If you extrapolate it to x-axis, that is what is called optical energy band gap from 3.84, this one, to 3.54. that ion tabulated in the miscellaneous. Okay, this is for what is called direct band gap. Whereas indirect band gap 1.5 to this one, this is 1.52. Maximum is 2.40. Okay, you see only 1.52 electron volt is sufficient to conduct electricity. Okay? That is what is called advanced functional materials. You can change the size of the group particles and condition will change. That is the property will changes. Okay, then some slides for young research students how to make piezoelectric crystals. Okay, that means you have to synthesize some crystals. Then you apply your pressure, test your pressure, then it generates electricity. That is called piezoelectric materials from polymer materials. You see, sodium potassium tartarate plus water heated to 180 degrees centigrade. Sodium bicarbonate or soda ash is added until to stop the what is called efflorescence or foam. After complete stop the foam, then you take it out and filtrate it and cool for a while. You will get a crystal. Then you have to subject it to what is called a multimeter. Then you will notice 13 to 14 volts of electricity in your multimeter. This can be easily synthesized in your laboratory. Okay, like that. That is called the piezoelectric material. If time permits, I will show you the what is called videos also. I will try to then make a gel salt electrolyte for battery applications. Okay, you take 300 ml distilled water with a magnetic stirrer in a beaker. Add 10 gram of potassium hydroxide. It is easily available in all the lab, even few lab also. Hydroxide, potassium hydroxide pellets. And add 20 gram of polyvinyl alcohol, more than 20,000 molecular weight, not below 20,000 molecular weight. It is available on polyvinyl alcohol. You have to heat it to 90 to 100 degrees centigrade. You see, this is total 300 ml water plus this one 3 times 30, 10 gram plus 20 gram. It exceeds 300 ml. Then you have to reduce, you have to evaporate up to 300 ml only. The constant volume should be remain 300 ml. That means you have to heat it to evaporate excess water. Only you have to restrict it to 300 ml. Pour the solution into mold or any container or petri dish. Evaporate to get a flexible film. It is a flexible film. Fill it and separate it and wash with water. Dry it. Okay. This is the flexible electrolyte film used for battery application. You can check it. Okay, you can connect a small bulb. You can connect the electrode. Definitely, it glows the what is called a bulb. It is also used for supercapacitors in electrical and electronic industries as energy storage applications. Okay, this is what is called some tips to the young scientists. This is the salt gel electrolyte for batteries. You take two beakers. Beaker A, 30 ml of water and 23 gram of zinc sulfate. It is also available in all the laboratories. And another beaker, that is B beaker, 30 ml of water. It is heated to 180 degrees centigrade on hot plate and add 4 gram of borax and 4 gram of gelatin. It is also available. Okay, add the solution, that is A, to the B. Apply this gel to the electrode. Any electrode, even you can make insulating material, wood or plastic. Then you have to connect the wire to a single cell or battery. Then you notice that it will sparks will generate That indicates that it conducts electricity. Even you can paste it on any material for that matter, either wood or cloth, paper, cardboard, glass, plastic. Okay, then it conducts electricity. If you connect it to multimeter, it measures 1.5 volt electricity. Okay, then it is an electrically conductive polymer from recycled plastic. Okay, waste polymer. We can dissolve it in a water soluble polymer. Okay, and some carbon black cannot, or if it is graphite, mix it together. Okay, this is one part. And liquid polymer, another part. You take it in three parts. One part is this much. To that you have to add either carbon black or graphite because it conducts both. Carbon black is a good conductor of heat and electricity. Okay, graphite is also uh, conductive material. Another beaker, that is same liquid, you have to add 3 to 4 spatula of silicon carbide, okay, to make a polymer solution. This is another one. And third one, the same recycled polymer solution. Okay, now you can do not add anyone. This is a plain polymer solution, waste polymer, recycled polymer. To this, either add carbon black or graphite, anyone. This is two component system. This is three component system, your liquid polymer and carbide, okay, sorry, silica carbide, like that. Then you have to take three papers or any three metal pieces, okay. You can dip in and dry and wash it with water. They act as a electrodes, carbon black, silicon carbide, and polymer solution. They are hydrophobic in nature, not hydrophilic. Sorry, this is hydrophobic. Washed with water and dried. Almost all materials can be coated with this polymer. You can coat it with any material, wood, sheet, paper, any this one insulating material. Solution surface becomes hard and glossy. The surface will become a hard and glossy finishing. Okay, gloss like finishing surface. So it conducts electricity. Okay, even paper can also conduct electricity. Okay, this is what is called some inks. Come to the sensors in polymer compounds in biosensors, biomedical applications. Take an example, polyacrylic acid and polyacrylamide. This is polyacrylic acid, CH2CHCOOH, the red. You see, CH2CHCOOH. This is acrylic acid. This is acrylamide, CH2CHCONH2. Okay. Take these two polymers, polyacrylic monomers, acrylic acid and acrylamide. You have to dissolve in the water. Okay. Then it forms initiators. There is some polymerization reaction. That is some initiators. Sodium metabisulfite and potassium persulfate. Then it forms a gel-like polymer. It is a polymer. You see this copolymer. This is a copolymer of polyacrylic acid and polyacrylamide. This is a hydrogen. Okay. It is used for drug delivery. It is a temperature and pH responsive hydrogen. It is a drug release only at 37 degrees centigrade only. 37 degrees centigrade room temperature. Okay, you see this is the T. T is 37 degrees centigrade. It is more than that. It's above 37 degrees centigrade. That is the upper critical solution temperature, UCHT. The hydrogen bond will broken. You see this is broken out. CH2COOH. CH2COOH. It's separated. That means this is hydrophilic. This is hydrophobic. The same material, just by varying 1 degree temperature, it becomes hydrophilic and hydrophobic. Okay, so it is a on and off drug release. It is only drug release where it attains 37 degrees centigrade only human body temperature. Below and above, it becomes a lock the drug. So this is what is called temperature responsive hydrogen sensors, biosensors. So we need not go for animal sacrifice drug for drug delivery. Where we want to drug release, not conventional method. This is called the novel drug delivery system. Do not eat capsules. Just where we target. There is no release any drugs unless where we want targeted diseased site. If you want the stomach at 2 pH, if you want to colon cancer at big intestine or colon, depending upon the region or specific disease site, we target the drug. Does not affect any other organs or tissues or cells. This is the what is called biosensors. Okay, temperature responsive. This is the hydrogens of polyvinyl alcohol, sodium halogenate. This is only swell in stomach only for what is called gastro retentive properties, gastro entities. Okay, like that diseases. This drug is very useful. You can load the drug at pH 2 only. It's a maximum swelling. There only it releases the drug. How it is possible means, you see this is alginic acid. This is alginic acid. It is extracted from seaweed. Where it is in the stomach, that is the ash environment, acid. It is acidity, that is pH is 2. That's why the fats and oils are digested in stomach only. Okay. This hydrogel is in stomach, it is deprotonated in higher acidic condition. So it loses COOH. You can it loses one H plus, then it becomes a COMS, COO minus. Whereas in stomach acid also it deprotonate. So that is also become an anion. So anionic, the repulsion takes place. So this hydrogel will swell in stomach only. There only it release the drug. This is also called the pH sensor hydrogel. These are comes under what is called advanced functional materials. Okay, advanced functional materials. That is a pH responsive biosensor for drug delivery. Okay, this is what is called piezoelectric material, pyroelectric materials, electroactive polymers. That means you have to subject it to electricity to the polymer with an enormous change in volume, length, breadth, and thickness of the film or angle. That means volume will increase. If you switch it on, it will become a contract. Okay, expansion and contraction very instantaneously. Enormous energy is released. Okay, that's why these materials are used for robotics. These materials are also called the artificial intelligence or smart materials. Okay, these materials are artificial intelligence. You see, this is actually a cathode. This is actually anode. These are the fluorine negatively charged what is called atoms. Okay, this is hydrogen soft point. When you subject it to electric field in one direction, so repulsion takes place, the increase in breadth. If you change the direction of the electricity or applied voltage, then it reverses, then attraction, then length is increases. So sometimes it is length, breadth, and volume also increases. That is volume increases. That's why this is called the electroactive polymers. It is used for artificial muscles and what is called robotics. If it is possible, I will show you what is called videos also. This is also what is called PVDO, polyvinyl fluoride. You can remember that it is a promising material for electrical, energy storage materials. Okay, electric, what's called energy harvesting materials. This is a promising material you can use it for so many electrical sensors and what is called rechargeable batteries. So many other applications, EMI shielding, RF shielding. Okay, like that. Please remember PVDF. It is a promising material for you, the physics students. It is a wonderful material. It is available, commercially available. Okay, you can in this direction, the length is in direction. If you oppose it, then its length is what is called increases. This is one of the what is called ionic polymer metal composites. You see ionic and polymer metal composite. You take a CMC carboxy methane cellulose, a polymer that is called the CMC carboxy methane cellulose. That is called as a sodium salt of carboxy methane cellulose. Understood that sodium is present in that. It acts as a counter ion. Sodium salt of carboxy methane cellulose or CMC one and the same. You see, this is the sodium ions. They are randomly arranged. Okay. If you make a film, okay, I show the film polymer film by solution cast technique. That means you have to evaporate the solvent, then you will get a film. You have to subject it to electric field or battery. Okay, you have to switch on. Then you see all the positive ions, sodium ions. These are the sodium ions. This is the electrode. Okay, this is anode. This is a cathode. When you subject it to electric field, all the sodium ions, they are randomly arranged. They were attracted to what is called anode. You see, there resides. Then it bends. Okay, how it bends? So, shape memory polymers. You can make, if you switch on, it becomes a strike. If you switch on, it becomes a bend. Bending on the strike line. These materials are used for what is called what's called uh, sutures, wound sutures, without contact with the patient and doctor. Only by UV light you can wound stitch can be possible. Like that. These are the electroactive polymers. This is the electroactive polymers. This is the counter ions. These are the electrodes. Last, okay. So intelligence system and robotics. This is the polymeric artificial eye. It is synthesized by Hong Kong University of Science and Technology. Okay, you see, this is artificial eye. This is artificial muscle. These are the it's called retina. It is made from nanowires. Okay, carbon nanowires. But carbon nanowires, they are not in the solid form. They are in the liquid form, like hydrogen. I told you know in the previous class, hydrogen. Okay, they act as a nervous system. Even we can synthesize muscle, artificial heart, okay, artificial skin. But artificial nervous is very difficult. But they are synthesized artificial nervous also. Okay, this is how the it is a biomimetic prosthetic eye. It is a electrochemical eye. It is also called the electrochemical eye using nanowires. It is an array of it's acts as a hemispherical artificial retina. It acts as a you see this is a hemispherical. Okay, due to the nanowire, the array of nanowires. That is a artificial retina, the 3D image sensor. It is published in Nature journal. It is a electrochemical high. It is used for robotics and the people with visual impairment they can use. Because it's what's called actually offer sharper vision than a natural woman. It is a very sharper vision than a natural eye. It includes extra functions such as the ability to detect infrared radiation also. Okay, it detects infrared radiation in darkness. Even from artificial eye, we can see in dark, in night also. That is one of the extra function. That's why it is also a functional material. You see, these nanowires were then connected to a bundle of liquid metal wires. It serves as a artificial nerves, which successfully channeled the light signals to a computer screen, which showed what the nanowire array could see. Okay, all the retina have a blind spot. Actually, we are have a blind spot. Okay, but these eye have no, blind spot. And actually, the normal vision is 6 by 6, but this artificial has high the capacity 20 by 20. Okay, this is very superior than our natural eye. Okay, so this is a healthy vision, and it is seen in the night also, stars and all. Its magnification is very high magnitude than natural eye. Okay, uh, it is a high density of photoreceptor cells than human retina. Therefore, in artificial retina can detect more light signals, therefore produce a higher image resolution than a healthy human retinas with 20/20 vision. Actually, 6 by 6 vision is the you know, a good vision, a good sight. Here 20 by 20, and it it detects infrared light also. Even you can see in the night. This is what is called this one. And finally, this is one polymer. I think it cannot be visible properly. This is a polymer material, ionic polymer. You can charge, you can build any charges on the polymer matrix. You can make anion, cation, non-ion, or amphitriotic 50/50. Any ratio for that matter, you can. This is used for what is called biomacromolecules. This is used for so many diseases. I will stop from this slide. Take an example, Alzheimer's disease. It cannot be cured. It lost memory due to the electrical signal. The you know the lose the contact. What is called it is disconnect the some nervous signals. So here what is called that is amyloid peptide. This is one of the peptide that is protein. Peptide means protein, CONH2. Okay, that is beta 142. It's the number. It is what is called a muscle like a fiber muscle. It is a fiber muscle. Okay, it is a linear in structure. It is positively charged. Then it is the deformation takes place. Instead of straight, it is a coil-like shape because of the deformation. Then it deposited, proteins are deposited on that. Then the contact will, the message in RNA, messenger RNA is disconnected. Like copper wire batteries, if copper is deposited, then contact is what is called the circuit is incomplete. No, like that it is a tracks are deposited, then the contact between RNA messenger, that contact will what is called takes place. Disconnect, this contact will take place. Then it is situated in brain. so it cannot be operated easily. But it can be cured by physics concept without any medicine operation. Just by electrostatic interaction, this disease can be cured. How? You take a anionic polymer to that. Then you just by contact with the what is called that peptide. Then electrostatic interaction takes place. It neutralizes the what is called the charges. It is a coil shape. Okay. Then it dissolves all the fats deposited on that. Then it is contact re-established. Then memory starts. Okay. The memory is due to the what is called the deposition of fat. Okay. Contact is poorer contact. That is the reason for Alzheimer's, not for 60 years. After 60, it is common for what is called what's called deformation of this protein. So this is anionic polymer. This is published in Biomicromolecules. Okay. I'll stop here. Thank you for listening. Any questions or points? Thank you, Radhika madam.
Yes, sir. Thank you so much for your nice presentation, sir.
Thank you, ma'am. I would say thank you because for inviting me to give me opportunity to share with you. It is more, I think it's inspire for students only. That's why I take a typical, a simple experiments for, students, interest regarding students interest regarding, not for you people or researchers. This is for physics students. Thank you, madam. Thank you.
Thank you, sir.
Shall I stop, madam? Stop.
Sudarshana, madam.
Thank you, sir. Thank you so much for your wonderful presentation.
Thank you, madam. Thank
Feeling
you.
gratitude and not. Thank you, sir.
Ma'am, please. Pardon me, madam.
Feeling gratitude.
Madam, not audible.
Sudarshana, you can go ahead, Sudarshana.
Yes, ma'am. Yes, ma'am. Feeling gratitude and not expressing it is like wrapping a present and not giving it. May I now request Mrs. T.N. Priyadarshini, Madam, Assistant Professor, Department of Physics, to propose a vote of thanks.
Good evening to everyone. I deem it a great honor and privilege to propose a vote of thanks on this memorable occasion. Let me first of all start by a resounding success. I would like to propose hearty vote of thanks to our chief guest, Dr. T. Demappa, Professor, Department of Postgraduate Studies and Research in Polymer Science, University of Mysore, Mandya, for gracing today's conference and making an excellent presentation on advanced functional materials. Thank you, sir. I would like to thank our management, CEO Madam and Principal Madam for providing an opportunity to conduct this conference. I sincerely thank our beloved HOD Madam, Dr. V. Radhika, Department of Physics, for her support and guidance. My hearty thanks to our staff members and participants of various universities, institutions who made today's session a grand success. Once again, I thank you all. I request all the participants to fill the feedback form. Thank you.
Priya, madam, please share the feedback link in the chat box so that the participants can fill it up.
Yes, ma'am.
Participants, kindly fill in that feedback link given in the chat box, and then you can leave the meeting. Tomorrow morning, please join by 9:45 a.m. in the same link. Thank you all.